Okay, 3.5, making connections with rational functions and equations. So it's some real world situations, word problems where these types of expressions, these types of functions actually do model real world situations. So the first one that we deal with is sound. And it explains to us what happens here. The intensity of sound is measured in watts per square meter, and it varies inversely as the square of the distance in meters from the source of the sound. So what does that mean? It means that the intensity, first determine a function to represent this relationship. Let I represent intensity. All right. Let I represent intensity. Let D represent distance. And then let's see if we can make sense of what this just explained to us. So I varies inversely as the square of D. So I is the dependent variable. It depends, the intensity of the sound depends on the distance that you're standing from the speaker. As the distance grows, the intensity declines. That makes sense. You stand further away, the sound's not going to be as loud or as powerful. But how it declines is that it is the square inversely with the square of the distance. So the formula that you work with there is I equals K over D squared, where K is a constant. So in questions like this, your goal is either, if you're given a formula for a specific situation, you'll be given K, and you'll be given either the intensity or the distance, and you'll have to find the one that's missing. Or you'll be given a situation and you'll be asked, what is the constant of variation? K is called the constant of variation. But typically you'll be given it. So if they said, your distance from a speaker at a loud concert, which is probably what we're dealing with here, you'll get the constant and then you'll get the distance and say, okay, what's the intensity, or how does the intensity change as you move backwards? Basically, if you move 2 meters away, the intensity is cut in 4. If you move 8 meters away, the intensity is cut into a 64th. Okay, inverse of the square. Anyway, now we kind of understand it. So let's look at this situation that we're in. The intensity of the sound from a loudspeaker at a distance of 2 meters is 0.001 watts per meter. So in A, I guess we can, let's follow your notes. This means that. Now substitute, we're not going to do this means that. Now substitute our values. I equals 0.001 watts per meter squared, and D equals 2 meters. Now all we do is sub those things in. So we've got 0.001 equals K over 2 squared. Multiply both sides by 2 squared, right? That's the same as multiplying both sides by 4. You end up with K equals 0.004. Which means that K is the constant of variation, which then means that the actual formula for this situation, therefore, the intensity of this speaker varies with respect to the square of time as 0.04 over D squared, where the restriction is D must be greater than 0, because you can't have 0 in the denominator. Okay, so we have created a function for this situation to represent this relationship. That's what we were supposed to do in A. Now we can graph it. Okay, this is a rational function. It's a basic rational function. It's all positive, and we know that it's only including values of d greater than 0. So distance was our independent, and intensity is our dependent. And basically, as you get, think of it this way, as you get closer to the speaker, intensity is going to be high. As you get further away from the speaker, intensity is going to come lower. So this curve looks a bit like that. Okay, if you wanted to know an exact point that it goes through, you could think of what is it when d is 1. So for instance, down here on your number line, if you have 1, 2, 3, when d is 1, the value of this function is 0.004. So right there you'd have 0.004. Give yourself a bit of context by adding some of the other points along the y-axis. Okay? Good, and now C. C says, what is the effect of having the distance from the source of the sound? So what happens if you're standing at 10 meters and then all of a sudden you move up and now you're only 5 meters away? What's that going to do to the intensity of the sound?
It decreases.
Oh, you're getting closer to the speaker.
Oh, you're getting closer.
So it varies inversely. It's going to increase. If your distance decreases, your intensity is going to increase. Well, how? It's going to be by the square of the d, the square of the distance that you've changed. So let's see what we do. We're going to first substitute 1/2 d in for d in our formula. So in C, we have the intensity equals 0.004 over half of d, and that's still squared. And we can simplify that on the right-hand side here. The numerator is still 0.004, but the denominator, if you take 1/2 and square it, you get 1/4, and you take d and square it, you get d squared. So you're looking at 1/4 d squared, or d squared over 4. Now, if you're not sure about the next little trick that's coming up, basically what you do if you're dividing a fraction by a fraction, you change it to multiplication and you flip the fraction. Do you remember that rule? So if we rewrite this, this is 0.004 divided by d squared over 4. We can rewrite that as 0.004 times, and then flip our fraction. Okay? So plug this back in as we simplify it. Basically, we are sitting at, and I'm not going to fully simplify it, we're going to leave this 4 out front. Multiplication is commutative, so I can write this as 4 times 0.004 over d squared. Okay? What did we do? We cut the distance in half. What was the result? Well, this is our original equation for I, the intensity. But when we cut the distance in half, the intensity is 4 times greater. Okay? When the distance is halved, comma, the intensity of sound is 4 times greater. The intensity of sound is 4 times greater. So what would happen if you went from 10 meters away to 2 meters away? How much louder, how much more intense would the sound be? So you're 5 times closer, so the sound would be 25 times more intense. The square of the distance.
I get what's happening, but math just looks awkward.
Math will do that sometimes.
Yep.
Okay, example 2. Diving time. The maximum time, this one is hard to understand, but scuba diving. Okay, the maximum time, T, in minutes, that a scuba diver can rise without stopping for decompression on the way up is defined by the equation T of D, so time with respect to depth, equals 525 over D minus 10, where D must be greater than 10, because you can't have, it wouldn't make sense to have a negative depth, in the denominator. Does that make sense? Anyway, this is our equation. I'm going to try to explain what this is meaning. Where D is the dive of the depth in meters, for the maximum time to be less than 30 minutes, how deep can the diver dive? So this is tying in things that we've talked about in the past days. We're going to consider all the cases, but since D is greater than 10, and that's going to make the whole denominator greater than 0, and we don't need to worry about what's happening to the left of 0 or below 0, then we only have one case to consider, okay? But what we want to find out is where this time is going to be less than 30 minutes. So the time is going to be less than 30 minutes. So we're going to take our expression, 525 over D minus 10, and we're going to find out where that is less than 30, time with respect to depth. Time less than 30 minutes, still dependent on depth.
Find what time it's 30 minutes and then say less than that.
Pretty much that's what we're doing. Yeah, we're going to solve for this equation and then find out which side of that solution satisfies our inequality.
So we look for like an exact number, like we can just go infinite digits, so it's really close to 30. So
since D is greater than 10, there is only one case to consider. Okay, since D is greater than 10, there's only one case to consider. It's going to be where this is positive. So as we're solving this, and we're going to multiply both sides by D minus 10, that's going to be a positive value, which means we don't need to worry about flipping the inequality. Okay, so we're going to be left with 525 is less than 30 times D minus 10. We're going to expand this in order to solve. The easiest way to do it is to, you could distribute the 30 to both terms, or you can now divide both sides by 30. So if you divide both sides by 30, you get on the left 525 over 30 is less than D minus 10. You add 10 to both sides. You get D is greater than 525 over 30 plus 10. Okay, 525 divided by 30 in your calculator, then add 10. You get D is greater than 27.5. So on your graph, if you've got 10, 20, 30, 40, we're looking for all of the place where this curve is above the line D is greater than, no, this is, yeah, sorry, T is 30. I did that wrong. We're down here for our D, because D is independent. T is dependent. So here we've got 5, 10, 15, 20, 25, 30, 35. On our curve, we're looking at the point where D is greater than 27.5 and T is 30. So that's our point that the curve goes through. 27.5, comma 30. We're looking for all of the values of D that get us to be less than 30. So we're looking at this range, less than 30, and we found out that then D in that range is greater than 27.5. This curve does something like this. And this is our line. T equals 30. So if the diver dives deeper than 27.5 meters, he's going to have to decompress more often on his way up. The time between decompressions becomes less as you dive deeper. Okay? The time between decompressions is less as you dive deeper. You have to decompress more often so that your lungs don't explode. Example 3, special cases. Sketch a graph of each function. Explain how they are special cases. So in A, we've got a marker that doesn't work. F of x equals x squared minus x minus 6 over x plus 2. And so you can carry out the same steps. We're going to factor the numerator and see if this simplifies. So that leaves us with x plus 2, x minus 3 over x plus 2. So now you can see that the whole function actually reduces into a linear function, x minus 3, because the x plus 2 and the x plus 2 cancel out. We know our restriction, though, is x cannot equal negative 2. Okay, so f of x reduces to a linear relationship, but x is not allowed to equal negative 2. So this creates a discontinuous at x equals negative 2. This is a line that is discontinuous at x equals negative 2. Basically means There's a gap. Okay, so when you sketch this line, it's just the line x minus 3, 2, 3, x minus 3, but there's a gap at x equals negative 2. And on the graph, you indicate that just by a little circle, an empty circle, a hollow circle. And we should tell exactly where that dot is. It's at negative 2. And if we put negative 2 in here, you get negative 2 minus 3. The value of the function, or where the value of the function can't be, is negative 5. So if you were doing the domain and range for this, you would say x, the domain is x belongs to the set of real numbers but can't be negative 2, and the range belongs to the set of real values, real numbers, but y can't be negative 5. Okay, so this is one special case. You have, it's discontinuous. Okay, it has a gap. Good. B. You have 2x squared minus 7x minus 4 over 2x squared plus 5x plus 2, g of x. Same thing, we're going to factor the numerator and the denominator. This would be factoring by grouping, so I'm going to skip that step and just give what the two factors are. In the numerator, you have 2x plus 1 over x minus 4. And in the denominator, you have 2x plus 1 times x plus 2. Now in this one, you can see that the first factor in the numerator and the denominator cancel each other out. So what you're left with is just x minus 4 over x plus 2. But don't forget your restrictions. X can't be negative 1/2. And x can't be negative 2. Now in this case, we've reduced this to a rational function in the form of ax plus b over cx plus d. I could just use this one, ax plus b over cx plus d. So the restriction that stays in the domain is still the asymptote, just like regular, but the restriction that got eliminated or canceled out becomes a gap. Okay, so it's still a simple rational function with just a binomial first degree expression in the numerator and a binomial first degree expression in the denominator. So it's going to take, and you could get some test values, etc., on how to draw it, but it takes this shape, but where x equals negative 1/2, there's a gap. Okay? I drew it wrong. Don't copy that because I didn't draw my asymptote. My vertical asymptote is at x equals negative 2. X equals negative 2. And the horizontal asymptote is at a over c, which is 1. Now my sketch will make sense. And we have a gap where x equals negative 1/2, which is about right here-ish. So the function represented here is g of x equals 2x squared minus 7x minus 4 over 2x squared plus 5x plus 2. And we have a gap here at negative 1/2. The value of the function at negative 1/2. You'd put negative 1/2 in for x, and you'd find out that it occurs at negative 1/2, negative 3. So it's a special case because it reduced to a rational function of this form, So one of the factors of x canceled out, and so it only has one vertical asymptote, but it has a gap at the restriction that got canceled out.